现在我是在学校的这个学院的休息室里面。现在早上9点多，我是10点开始正式毕业答辩，所以我现在正在准备。也应该说也不需要什么准备了，毕竟已经准备了这么久，现在就是在等待开始答辩的那一个时刻。希望一切都顺利吧，记录一下答辩的这一天。
Thank you everyone for joining my PhD defense today. And I'm Jiawei Wang, and today I will introduce what I have been doing in the past 4 years as a PhD student in the Department of Civil Engineering. And my research aims to explore the potential benefits of artificial intelligence in traffic domain. And in this thesis, I specifically target how to design a multi-engine reinforcement learning for public transport vehicle fleet control. I wonder whether have you ever been waiting for a late bus and all of a sudden 2 or 3 buses arrive at the same time? That's called bus bunching. The bus system is unstable in nature, and any uncertainty from transit demand or the traffic state may bring some delay for the bus. And any delay has the potential to be as a fate down the road, because if a bus gets delayed, there will be more passengers waiting at the next stop, and the extra passengers boarding time will make the bus even later. So there will be a vicious circle. And as a matter of fact, the bus bunching has been a long-standing problem worldwide, and in this case, the passengers often suffer from long waiting times, and the bus may have imbalanced occupancy. So there may be a huge waste of public transport resources. As a result, we need bus control strategies in the transit operation to avoid this bus bunching and provide reliable and efficient service. Nowadays, more and more studies begin to utilize real-time information to elevate the control performance. But according to the private studies, there are some drawbacks. First, they cannot utilize each decision as prior information, so their parsec may be less efficient. And second, their parsec cannot efficiently consider the long-term effect, which results as the optical parsec. And the last is that their parsec cannot update based on the real-time feedback, which results in a static framework. But advanced reinforcement learning provides a better solution to such kind of control problem. You can see that by exploring the action, making action based on a well-defined state, the process of obtaining a good parsec will be more efficient. And when we consider the cumulative reward, the framework can take into account the long-term effect in nature. And in addition, by continually interacting with the environment, the engines can keep updating its parsec towards new situations in a model-free setting. Finally, if we extend the single engine to the multi-engine setting, then we will have a greater opportunity to develop an efficient control framework with a cooperative architecture. However, some challenges remain if we want to apply these methods in the transit control domain. The first is efficiency, which results from the complicated dynamic of a multi-engine system. During training, the parsec of each engine will be evolving, which results in so-called non-stationary and brings large variance during training. And in addition, the contribution of each bus engine in the system is not determined at some time. So if we cannot figure out how much engines control action contribute to the system's performance, they cannot evaluate and update their parsec accurately, right? And another issue is the transferability. It means the ability to generalize the parsec learned in one environment to another unseen environments. It is important because we want to ensure that the bus lines, the parsecs learned in one bus line is also available in another bus lines. And at the end of the day, we have to pay attention to the robustness. The state and the reward are not stable at some time, but we want our engines to give effective control in these situations. It is important because there is much randomness or uncertainties during transit operation. So in this thesis, we identify and want to address these 3 challenges. We want to propose an efficient and reliable multi-engine reinforcement learning framework for bus holding control. And to this end, we decided the 4 research steps to address the challenges step by step. Now let's first introduce our first research. How do we design a cooperative multi-engine reinforcement learning framework for efficient bus control? At first, we need to map the transit system into the reinforcement framework. And in this study, we can regard the bus as the entrance and the transit system as the environment with which the bus will interact. During operation, the bus will observe a state at its arrival at a bus stop, and it will make control action based on this state. And it will receive a reward to evaluate this control action at its next arrival at a bus stop. So with this process, we can define the key elements of the reinforcement. The first is the state. The bus makes control actions based on this state, so we want it to be as informative as possible. In this study, we use the forward and backward habit of the bus to identify its location, and we also use the number of waiting passengers to highlight the event information. And the next step is to define the action. The engines will use this action to interact with the environment. And in this study, we use the holding control in our framework because, as pointed out by the prior studies, the holding control is the one that can not only make the passengers less frustrated, but also provides better maneuverability to the free operation. And finally, we need to have a reward function. The engines will learn the policy by maximizing the cumulative reward. So we want it to be in line with our goal. Let's say avoid bus puncturing. So we design this reward function in this study. The first term directly encourages heavy iteration between the forward and backward bus, and second term encourages relaxed holding time. And this reward function is kind of a trick to encourage cooperative control because you can imagine that if each bus in the system can maintain an equal heavy between its forward and backward bus, then the heavy will be consistent among the system, and the function won't happen. And then how do we train our engines to learn the cooperative control in this sector? And here we adopt the classic multi-engine reinforcement framework, the MARL, and use the actor critic as the optimization architecture. Here, the actor is used to derive the control action based on the state, and it can be modeled by a DPU network. And we have a critic to evaluate the actor's control action based on the state and the other engine's actions. By doing this, we can release the assumptions of other engines' policies during training, and we can reduce the variance to some extent. And different from the traditional MARL, we introduce a joint action tracker here to approximate actions based on some global information. In this way, we can reduce the training complexity during the training procedure. And okay, and let's see how do the proposed methods behave compared with other traditional baselines. Here are the bus trajectories under different control strategies. And the black dot here indicates the holding action, and the deeper color means the longer holding time. We can see that the proposed models can avoid the bus puncturing with max holding time. And we owe this improvement to the cooperative control learned from our framework. But one point here is that, as I mentioned before, we train our engines using a fixed number of actions from another bus system. This control actions may not occur simultaneously in real applications, so which may limit cooperative training. So this question brings us to our second research. Can we further improve our cooperative framework when control is asynchronous in most cases? And how do we improve the transferability of our framework? And to do this, we first introduce a global reward function. Here, the first term of this reward directly encourages heavy consistency. So the engines should learn the cooperative personnel because they are sharing the same goal, right? And the next is that when the bus is waiting for the feedback of its last control action, there may be asynchronous control events from another buses. These control events are important because they are related to the accurate feedback for which the bus is waiting. So to utilize these events in our study, we designed an event graph to incorporate them. And specifically, you can see this figure. And for the Eagle bus I here, there are 3 control events when it is waiting for the feedback of its last control action. So we highlight these 3 control events with 3 incoming edges, and we can formulate a graph with respect to this Eagle bus. And we can use this graph to provide a clear structure to consider the events. And to utilize this event graph in our multi-engine reinforcement framework, we can adapt the traditional active critic with an inductive critic. It is used to better approximate the effect of each engine's control action. Specifically, we have an ego critic to evaluate the parsing of the ego bus, then we design an event critic to account for the contribution from another buses. In this way, we want to address a common issue in the multi-agent reinforcement, that is the credit assignment. And inspired by inductive learning, we use a graph neural network to handle the asynchronous event graph. And in this way, we can handle a determined number of control events during training procedure. And as the control feedback from the environment mainly results from the control of the ego bus and another buses. So we approximate this feedback with this sum, the sum of these two critic. And we decide this objective function to train this critic. One point here is that we introduce two regulation terms to encourage inductive learning because if there is no other control events when the bus is waiting for the feedback, that the marginal contribution from another buses should be as low as possible. Okay, so by far we have addressed credit assignment issue in the asynchronous multi-agent reinforcement. And in experiments, we first evaluate our models on a trained bus line. And we can see that proposed models has the potential to enhance the cooperative framework with better systems regularity. And to further validate its transferability, we directly apply our models on 3 bus lines in our retraining. And again, we can see this metric table that the proposed models can improve the system's regularity compared to their baselines. Because these models are trained in given a determined number of control events, it turns out that this setting can help to transform to the model to the bus lines where there are different number of bus stops. Okay, so by far we have proposed methods for efficient and transferable bus control. The next question is, how do we consider the robustness? It means that the engines should still give effective control when there are some uncertainties or the randomness. For example, the transit demand uncertainty in which there is like a demand surge at some stops, or the traffic state uncertainty in which the bus is severely delayed due to some accident, or something like that. And to do this, we introduce distributional reinforcement. And the idea is that when we use reinforcement for the bus control, the randomness or the uncertainty mainly comes from the reward of the action, the state transition, and the long-term effect. So with distributional reinforcement, we can learn an action value distribution to evaluate the parsing. In this way, we can account for the randomness during the transit operation. And to learn this action value distribution, we adopt the idea of increasing quanti-learning. The idea is very simple. We can approximate the action value distribution with a quanti function, and then we learn this quanti function using quanti refraction technique. And with this action value distribution, we can transform the traditional critic to the distributional critic. And by doing this, we can incorporate the uncertainty or the randomness during transit operation into the evaluation of the parsing. And to further conduct efficient training, we introduce the distorted action value function here. And the idea is that we can distort the evaluation based on introduce distorted function. And in this way, we can incorporate the confidence or the preference into the evaluation of the parsing by using different distortion functions. In other words, we can regard the distortion weights as the confidence on the actor's contribution. For example, the risk-seeking distortion weight means that we are showing high confidence on actor's contribution to the system's performance. So with different distortion weights, we actually can train the actors with different preference or confidence. By doing this, we can adjust the randomness in the system and at the same time make good credit assignment, as I mentioned before, a very common use in potential reinforcement. Okay. Instead of using a fixed distortion weights, we design a method a technique of method reinforcement to update the distortion weights during the training procedure. So we can see the whole picture of our framework. We have a method to produce the distortion weights for the distributional critic. And this critic will use the distortion weights to provide a vector evaluation for the actor to update its policy. And in experiments, we find that the proposed models can rapidly handle the uncertainty during the transfer operation. And one point here is that when we train our models using fixed or no distortion rates, the performance will be less satisfying, which demonstrates the importance of the method in our framework. And interestingly, we can see that when we train our models using an unconfidence distortion rates, the models will pay more attention to the holding time instead of the system's regularity. This kind makes sense, right? Because at this time, the distortion rates place less confidence on actors' contribution to the system's performance. And in addition, we validate our models on some defined anomalies. For example, the transit domain anomaly and the transit demand anomaly. And we visualize the bus trajectories before and after these anomalies under different control strategies. And we can see that the proposed models can recover the system's regularity more effectively after the anomaly occurs. In the end of this project, we extend the scope of our research in the multi-line scenario. And if our loss of generality, we consider the multi-line with a shared corridor. And we start this research by thinking about, can we extend our single-line control framework in the multi-line setting? And we suggest two critical elements. The first is the state, and the second is the reward. As I mentioned before, the bus will give a good state to make a reasonable decision, and a good reward is beneficial to guide the parsing towards our goal. So for the multi-line state, we introduce 3 turns to consider the information from another bus lines. And for the multi-line reward, we also introduce another turn to encourage heavy equalization between different buses from different bus lines inside the shared corridor. And now we can see that there's 3 reward sources in this reward function. So we regard it as a multi-objective problem. And the issue is that can we further improve the training performance given the multi-objective reward function? And here we adopt a very interesting idea that's learning from the preference. It's also kind of a human-AI cooperation. The idea is that we can formulate the operation of a bus in a whole day as a trajectory. And we suppose that there is an expert to evaluate this trajectory. Then the trajectory with better evaluation should be given higher rewards by tuning the rates. For example, if the expert prefers less average income, then the trajectories with less average income should be given higher rewards by tuning the rates. Mathematically, we can randomly compare a pair of trajectories using a probabilistic model like this function, and then we can derive the posterior distribution from this model for the reward weights. And then we can update these weights using any approximation methods. In this study, we use the MTMC to update the weights during the training procedure. And here is the whole picture of our framework. First, we have a multi-engine reinforcement learning as a backbone, and then we have a preference learner to learn the preference from an expert, and to provide an informative reward for the actor to update its policy. So we can intuitively update these 2 procedures. And in experiments, we design some traditional baselines and appraisal models to validate that each enhancements in this framework, the multi-line state, multi-line reward, and the preference learner do improve the single-line control framework. And in addition, by updating the weights towards better average rating time, as we decide an expert by doing this, we can further improve the system's regularity-related metric. And in addition, we also visualize the bus arrival patterns under these control strategies. And here, the deeper color means more serious bus bunching, and the bus stops inside this red frame indicates the bus stops inside the shared corridor. And we can see that the proposed models can avoid bus bunching more effectively, no matter inside or outside the shared corridor. Okay, finally, as a summary, in this thesis, we propose a cooperative multi-engine reinforcement framework to achieve an efficient bus holding control. And to our knowledge, we are the first to introduce a synchronous multi-engine reinforcement link to achieve high transferability in bus control based on the reinforcement link. And we are also the first to introduce distributed multi-agent reinforcement learning to address robust bus holding control. And finally, we extend the scope of our research in a multi-life scenario by efficiently addressing the multi-objective multi-agent reinforcement learning problem. For the future work, we expect that there will be a large network validation and thinking about how to take measures to bring the reinforcement learning into real-world application. One point here is that we may define a high-quality classifier process pipeline for any downstream application. And last but not least, we also expect the more connections among the traffic entities in ITX, because in this way we can develop a more comprehensive control framework towards better interoperability. Okay, that's the publications during my PhD procedure, and thank you, my supervisor, Professor Li Junsheng, and the committee members for the time today. I also want to thanks my friends for this beautiful journey, and thanks my family for support. Thank you, everyone.